Alright, we now arrive at the third and final installment of our long-winded lecture on atoms, molecules, and ions. And what can we possibly learn yet that we haven't already covered? Well, here it is. After today's lecture, you should be able to distinguish between ionic and molecular compounds, generate empirical formulas for ionic compounds, generate names for ionic and molecular compounds, memorize the following ions' names and formulas, interconvert between ionic and molecular compounds' names and formulas, and memorize the names and formulas of the following strong acids. But first, our chemistry cat of the day from quickmeme.com. Okay, today's quick meme isn't actually a cat, but instead is a photo making fun of the naivety of college freshmen. Hence, I call this college freshman of the day. I like this particular one because the guy pictured here kind of looks like one of my brothers-in-law. Here it says, "My first chem exam is tomorrow. I did fine in high school without studying. 12 out of 100. It's funny because it's true. And don't you forget it. You have to study to do well. In our last lecture, we learned about the difference between ionic and covalent bonds. As discussed, in their journey toward feeling like a noble gas, when a metal and a non-metal bond, the metal more or less transfers its valence electron, or electrons, to the non-metal. This process forms two ions, a cation, which is a positively charged ion, and an anion, which is a negatively charged ion. This type of bond is called an ionic bond. In contrast, when two nonmetals bond, they don't transfer electrons, but instead just share them to help each other feel like noble gases. This sharing can be very even and fair if the two atoms are more or less equally electronegative, or very imbalanced and one-sided if one atom is much more electronegative than the other. This type of bond is called a covalent bond. Which brings us to some cool new terms. Molecules that have all covalent bonds in them are called molecular compounds. Molecules that have all ionic bonds are called ionic compounds. So let's take a look at this problem. Of the choices below, which one is not an ionic compound? To answer this, we just have to look at each compound and ask ourselves, does this compound contain a metal bonded to a nonmetal? If so, then it has an ionic bond and is an ionic compound. If not, then it has only covalent bonds and is hence a molecular compound. I'll let you tackle this one on your own. So when a metal and a nonmetal get together to form an ionic compound, they have to do it in the right amount so that they balance out each other's charges. For example, let's pretend that we had a metal A with a charge of plus X getting together with a nonmetal B which has a charge of minus Y. How many A's will have to combine with how many B's to give us a balanced ionic formula? Although we could do some convoluted math here if we wanted to, there's a simpler way to generate an ionic compound's formula. And what is that way? Why, all we have to do is just use the X as a subscript for B and the Y as a subscript for A. This gives us the formula of A subscript Y, B subscript X, as indicated here. In doing this, we remove the negative and positive signs from X and Y, since subscripts don't have negative or positive signs. Now, I hope that seems simple enough. If so, let's see if we can work out an example by going to the doc-cam.
I know I'm rambling, but let's go ahead and get to our problem you originally asked. You were asking about this question, number 35. We see that we've got these options, sodium fluoride, Na2F, and A2F. NaF2, D is Na2F3, and E is Na3F3. Now, first things first. I'm going to write Na, and I'm going to write F, and I'm going to write in big letters expected charge. Since you asked this, I'm going to ask, looking at your periodic table, what would you expect sodium's charge to want to be in order to make it feel like a noble gas? And what would you expect fluorine's to be?
1 plus on the sodium and 1 minus on fluorine.
That is totally correct. So there's a magical trick that I'll teach you in the next lecture video. If you write the charges above here, rather than having to do complicated math, what you can do is ignore the numbers, the positive and the minus, and just use them as the subscripts on each other. Na1, F1, which is another way of just writing NaF. So that would be the answer. Let me show you another example, actually. Let's do magnesium and nitrogen. That's a good one. Expected charges on those guys. So what I can do is I can write down Mg plus 2 and nitrogen minus 3. In order to predict the empirical formulas, I just take a 2 and put it there, and I take a 3 and put it there. And I get magnesium 3, nitrogen 2. Does that make sense? Each of these magnesium atoms has a charge of plus 2, and there are 3 of them. So the overall charge I've got here is 3 times plus 2, which is plus 6. Does that make sense? Each of the charges of the individual nitrogens is minus 3, and since I have 2 of them, the overall charge of those is minus 6. Those balance each other out. So you can mathematically do that in your head if you want to get the right answer, or you could just do this little trick. Ignore the negative and the positive and just use this as the subscript for the one and this is the subscript for the other. And you get the correct answer.
So let's see if you can do this problem on your own. Predict the empirical formula of the ionic compound that forms from magnesium and fluorine. And here's another one. The charge on the copper ion in the salt CuO is what? Thus far, we've seen that it's pretty easy to predict what charge an element will be when it becomes an ion. For metals in groups 1a and 2a, their ions charges will just be plus 1 and plus 2, respectively. For aluminum over here in group 3a, its ions charge is just plus 3. Conversely, for nonmetals in groups 5a, 6a, and 7a, their ions charges respectively become minus 3, minus 2, and minus 1. The question now becomes, what about metals in the middle of the D block, the region indicated here? Well, as it turns out, many of the metals in the D block, which are called transition metals, can exist as ions with various different charges depending on what they're bonded to. For example, iron, abbreviated as Fe and shown here, can exist as either a plus 2 ion or a plus 3 ion depending on what it's bonded to. Similarly, copper, abbreviated as Cu, shown here, can exist as either a plus 1 or a plus 2. Similarly confusing and often unpredictable trends arise all over the transition metals in the D block. Now don't worry, I'm not going to make you memorize all of the different charges that each individual D block element can attain. I do, however, just want you to understand that there is a lot more variety in them, because this will become important in the next slide, which is the slide shown here. When we name ionic compounds like sodium chloride, we follow these rules. The atom on the left, which is the cation, sodium in this case, is just given its regular name, if it's not in the D block. Now, if it is in the D block, then it's given its regular name with a Roman numeral after it to indicate its charge. I hope that makes sense. Remember that D block elements sometimes can have varied charges. So for those elements, if they are the cations, we have to specify what positive charge they have by putting brackets next to their name, and inside the brackets we put a Roman numeral indicating what charge they have. The anion, Cl in this case, is given its regular name, chlorine or fluorine, except at the end of it it's replaced with the suffix "ide", so in this case it's chloride. So this molecule will be called sodium chloride. Which brings us to some gnarly problems. The correct name for MgF2 is what? Now let's think about this for a second. In order to properly do this problem, we have to look at Mg and ask ourselves the question, is this atom, Mg, in the D block? Now as it turns out, it is not. So where is it? Well, it's in group 2, which means that it has a positive 2 charge as a cation. What is the name of Mg? Why, it's magnesium. So using the rules that we had in the previous slide, you'll note that the first part of the name is going to be magnesium. Now what about this F here? What is F? It's fluorine. Now note that when fluorine becomes an anion in an ionic compound, as this one is here, it now gets the end of it replaced with the suffix "ide." Hence, this molecule is called magnesium fluoride. Now note that this subscript 2 next to the fluoride doesn't change the name in any way. We don't have to say difluoride or bifluoride or something like that. It's just magnesium fluoride, which is letter E. Let's take a look at the next one here. The correct name for FeCl3 is what? Now we're first of all going to look at Fe and ask ourselves, is this element in the D block? Now you'll note by looking at your periodic table that indeed it is. Now because this element, Fe, is in the D block, we have to put Roman numerals next to its name to indicate what its charge is. Now what is the name of Fe? That element is iron. So to start this element's name out, we're going to say iron. The question is, what charge does Fe have to have? Well, in order to balance out, we have to look over here at the anion. Chloride, you'll note by looking at the periodic table, is going to want to have a -1 charge. Each of these chlorides is going to have a -1 charge, but note that there are 3 of them. Hence, the overall minus charge that the Fe, the iron atom, has to balance out is -3. Hence, this iron has to be a +3 charge. So the final name for this molecule is going to be iron, with Roman numeral 3, chloride. Now note, we don't have to say trichloride or dichloride or anything like that. For ionic compounds, we do not use any prefix di, tri, or anything like that associated with this subscript. So the final answer is iron 3 chloride. Now I hope that makes sense. We have to put the Roman numerals there to distinguish between iron 3 versus a circumstance where we might have iron 2. And here are some more questions. The correct name for Al2O3 is what? And I'll let you figure that out. And another one, the correct name for FeCl2 is what? Now you'll note, distinguishing this molecule from the last one we had in the previous slide, the iron here has to be a +2 instead of a +3. Hence, the answer to this question is going to be iron 2 chloride, which is answer A. Now we've talked thus far about how to name ionic compounds, which are compounds that contain ionic bonds. But how do we name molecular compounds? That is, compounds that contain all covalent bonds. Well, when we name molecular compounds, like SO2 or CH4, for example, we follow these rules. The atom on the left is given its regular name. Now, if more than one atom to the left is present, then we preface its name with the prefixes di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, and so forth. We don't use the prefix mono for the atom at the left. The atom on the right is given its regular name, except that its last few letters are replaced with the suffix "ide." When more than one atom to the right is present, we preface its "ide" name with the prefixes mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, and so forth and so on. This brings us to a great lecture problem that I really wish I would have included in our problem set. Oh well, here it is. Given the name or chemical formula, whichever one isn't given here, for each of the following molecular compounds. Now I'm not going to do all of the examples shown here. I just wanted to take a look at maybe one or two. Let's look at this molecule right here, SO2. What name would I give that? Well, given the rules that we had on the previous slide, we look at the atom on the left, which is sulfur, and we note that because it's the atom on the left, even though there's only one of these atoms, we do not use the prefix mono. We do use the prefix mono for atoms on the right, where applicable. So the first part of the name is sulfur. The second part of this name is going to be this oxygen. Now, because it's the atom on the right, we end its name using the suffix "ide." So this would be kind of sulfur oxide. However, we also remember that the oxygen has this subscript 2 next to it. So we have to put the prefix di before we put the oxide. So the final name for this molecule would be sulfur dioxide. Let's take a look at this example down here. We've got a chlorine that's the atom to the left, and we've got an oxygen that's the atom to the right. The chlorine's name stays exactly the same, but because it has a 2 as a subscript, we have to put the prefix di before it. Hence, the name of this is going to start by saying dichlorine. Now what about the second half of the name? Well, the oxygen is going to be the guy on the right, so he has to end with the suffix "ide." However, because he has 3 as a subscript, we have to put tri in front of his name. Hence, the final name of this compound is going to be dichlorine trioxide. I hope that makes sense. If you guys want to, you're welcome to work out the rest of these problems and see if you can do them. They will be excellent practice and good preparation for future exams on this subject. This brings us to a subject that might totally blow you away. Okay, as it turns out, there are some ions that are made up of multiple atoms bonded together. These are called polyatomic ions. Now, most polyatomic ions have weird and non-systematic names, so you just have to memorize them. I want you to memorize the names and formulas of the following polyatomic ions. There's this famous cation called ammonium, which has the formula NH4 and a charge of +1. And there are these 7 anions, which with the individual formulas and charges shown here. Now, I know this might seem cruel of me to make you memorize all these names and formulas, but I know you can do it. So this subject sometimes confuses students. For example, students sometimes think that they need to pick apart the nitrogen and the hydrogens in NH4+, but that's just not true. When you're making a formula using a polyatomic ion, one of these guys shown here, just treat the NH4+ as if it were an Na+ or a K+, for example. When you write ionic formulas, don't treat the NH4+ as a separate N and 4 H's that you all have to deal with. Similarly, when you're writing a formula, just treat all of the polyatomic anions, such as acetate or cyanide, for example, as if they were just a Cl- or a Br-. Don't let the extra atoms scare you. Going back to this, if I have a polyatomic ion, I just view the entire ion as being like an A plus X or a B minus Y. You remember us doing this before with our earlier ionic examples. We do the exact same thing, except we substitute A or B with the entire formula of whatever the polyatomic ion is. Now, to reduce confusion with polyatomic ions, we usually place parentheses around them to separate them from their subscripts, Y and X, like this. Let's take a look at this example. Give the empirical formula of the following molecules. I have 4 examples you can look at: ammonium chloride, iron 3 cyanide, magnesium sulfate, and ammonium sulfate. And I will address a couple of them right now. Let's start with the first one, ammonium chloride. To do this one, I'd like to begin by making a small table like the one shown here. I now write down the target name for which I'm trying to devise my formula. In this case, ammonium chloride. Now, what is the cation's individual name? Why, it's ammonium. And what is its charge? +1. What is the anion's individual name? It's chloride. And what is its individual charge? It's -1. We now return to this old format of A that has a +X charge combining with B that has a -Y charge. We now have to apply this to this specific example. What is my X, my A, my B, and my Y? Well, in this case, my A is NH4, my X is +1, and my B is Cl, and my -Y is -1. Note how I put parentheses around my NH4 here just so that I don't get the 4 confused or mixed up with the +1. Now, doing the same transposition of charges, turning them into subscripts like we've done in the past, I can see that my final answer is going to be NH4Cl, ammonium chloride. So let's do another one. In this particular example, the target name for which I'm trying to devise a formula is magnesium sulfate. What's the cation in this substance? Well, it's magnesium. Its charge is +2. What's the anion? It's sulfate, which has this formula, and that anion's charge is -2. Going through the same process as before, I basically just consider the A here to be Mg, magnesium, and the B to be SO4. My X here is +2, and my -Y is -2. Hence, I hope you can see that I'm treating the whole SO4 with parentheses around it as just being like the letter B. As I do the same transposition from my charges to subscripts, I can see that my final answer ends up being MgSO4, magnesium sulfate. Now let's do just one more, just because it's so darn awesome. The substance I'm trying to devise a formula for in this case is iron 3 cyanide. The cation is iron, whose formula is shown there. His charge is 3+. The anion is cyanide, which has a charge of -1. In this particular case, the letter A is Fe, and the letter B is Cn. Now remember, I put parentheses around that, and I just treat all of Cn as if it were just one element, B. The plus X in this case is +3, and the minus Y is -1. I now apply my transposition of charges to become subscripts, and I end up getting FeCN3. Now keep in mind, I put parentheses around the entire formula of Cn with the 3 as a subscript there to indicate that there are 3 cyanides. If I didn't have those parentheses there, it would be saying that there are 3 nitrogens but only 1 carbon. Hence, I have to keep my parentheses around that to indicate that there are indeed 3 total cyanides, each of which has a -1 charge, and all of those combined give a total negative charge of -3, which is balanced out by the +3 charge on the iron. I hope that makes sense. Now I ask, can you go backward? That is, if you're given the formula, can you produce the name? Now I'm not going to give you the answer to this question here, but will instead let you attempt to do it on your own. We now arrive at our final topic for the day, and for this chapter, that of naming acids. This topic is pretty straightforward. As it turns out, there are 7 strong acids whose names and chemical formulas I require you to memorize. They are HCl, which is hydrochloric acid, HBr, hydrobromic acid, HI, which is hydroiodic acid, H2SO4, which is sulfuric acid, HNO3, which is nitric acid, HClO4, which is perchloric acid, and H3PO4, which is phosphoric acid. Which brings us to some final naming problems I have for you. Give the name or chemical formula, whichever one is missing, for each of the following molecular compounds which all happen to be acids. So that's the end of this lecture. Please tune in next time as I begin our discussion on Chapter 3's coverage of stoichiometry. I hope you've had an enjoyable time. Until then, I bid you a fond farewell.